Okay, thanks. Good morning. So today, just to give you a quick overview of what's coming up, we have Lara, first of all, who's going to be starting the Calabi-Yau machine learning course. Then the other talk before the coffee break is Steve Abel, who'll be continuing with his meta heuristics from yesterday. After the coffee break, we have Alexander, who'll be telling us, I believe, about Fano varieties, and that's in preparation for some machine learning in that context later on, starting tomorrow. Then in the afternoon, so after lunch, we have the first tutorial for the Calabi-Yau course. And then after refreshments, there's the tutorial for the quantum annealing, so for Steve's course again. So that's what's coming up today. And so without further ado, first up, we have Lara Anderson from Virginia Tech, and she's going to start by telling us about Calabi-Yau manifolds.
Hi, everybody. Thank you very much to the organizers for putting together an excellent school so far. I'm very happy to get to participate in the dialogue on this subject because I think it's a really exciting one. I should say up front that unlike the speakers yesterday, Fabian and Steve, for example, who've had quite a long program of research in applying machine learning to various aspects of physics. Personally, I am a string theorist who's only come to machine learning much more recently and out of necessity. So I work within the subject of string compactifications, which I'm going to sketch for you very briefly. And as I'll argue, there are some very big prizes in terms of difficult nonlinear PDEs that we desperately want to solve in this subject. And so machine learning tools are a very attractive avenue towards an answer that we've been looking for over 30 years. Just to give you a brief plan for this course, there's going to be 5 lectures. And the history on this is that James and I and Fabian and several collaborators recently wrote a paper about Calabi-Yau metrics using machine learning. And then those tools were further developed and implemented by Magdalena and Fabian and Andre Lucas and collaborators into a very nice package that implements a bunch of these tools and makes them very easy to use. So we decided to combine forces. This course is going to be jointly lectured by myself, James, and Magdalena. And I wanted to give you just a brief overview of what we're planning to do with the lectures. So today there's going to be no machine learning. I'm going to be setting up some background geometry. And then the next 2 lectures are going to be starting to introduce numerics into this problem, talking about metrics on Kähler manifolds. This is going to be James. And then the actual machine learning implementations and the package that was developed to make this easy to use is going to be covered by Magdalena. So that's the rough outline of what's going to happen, and that's, yeah, in the schedule. So the goal for today is to review Calabi-Yau geometry in as minimal a way as possible. So I could give a week-long lecture course just on Calabi-Yau geometry. That would be very boring for many people in the audience who already know this very well, and also not so useful for many people who don't work in this subject. So I want to try and just give you sort of the bare minimum of important pieces to understand how this fits together. And if string theory or Calabi-Yau geometry is not your usual cup of tea, let me try and phrase this in terms of a bit more like, why would you care? The big goal is going to be machine learning for PDE solving, basically, hard nonlinear PDEs. And here's the real catch, in curved spaces. So we're all used to calculus in flat space, but of course, many problems have very non-trivial topology associated with them. And so if you're doing calculus in curved spaces, this is of course the realm of differential geometry. And you need to be able to package this in a way that you can use machine learning implementations to attack. And to do that, you have to understand a little bit about the curved geometry in play. So to do this, we need to understand the elements of geometry that are important in their own right, and also important to teach to a computer. And the other thing I want to cover is why we're actually interested in this problem. So why is this a big prize in string theory? And why are problems like this appearing in many other avenues? I should say that in other realms of physics, so just this as an aside, I'm going to be mostly focusing on the application of Calabi-Yau metrics to string theory. But there are other avenues where Calabi-Yaus appear and their metrics can be important. For example, in the vacua of supersymmetric field theories, Calabi-Yau geometry appears. Also in a lot of recent work in the study of amplitudes. In quantum field theory, Calabi-Yau geometry has also made surprise appearance. So this pops up in various locations, and many of these tools can be generalized beyond the Calabi-Yau context. So first, what is a Calabi-Yau? So the definition, which we're not all going to understand as I write it down, and then I'll try and define the pieces, is a compact Kähler manifold with vanishing first term class. So X is our Calabi-Yau. And this admits a Ricci flat metric. So I have to tell you what these ingredients mean, what it means to be Kähler, and also why the Ricci flatness is important. A bit of history. Calabi-Yau, the name arises because in the 1950s, a mathematician, Eugenio Calabi, made a conjecture that Ricci flat metrics should exist on manifolds such as this, and this was proven by Yau in the 1970s and resulted in a Fields medal for a proof that a Ricci flat metric existed, but that proof was not constructive. So Fields medal for just showing the thing existed. No one has analytically written down such a metric. So this is why this is a big prize. It's very important for string theory, as I'll argue in a second, and numerics are really our only avenue towards this answer. So let me try and sketch why we care about this. So in string theory, and the subject is string compactification, the 2-second version, Nova Special, is that string theory is an incredibly powerful framework for combining all the interactions that we see in nature with gravity as a consistent quantum gravitational theory. Whether that quantum gravitational theory describes the universe we actually live in is very much up as a question and open to debate. But it's an interesting framework and a playground to look at gravitation coupled to other interactions in a consistent way. String theory is extremely powerful and potentially very predictive in terms of what particles and interactions it could say exist if it did model our universe. But it comes with a big catch, which is that it is formulated in more than the 3+1, 3 spatial and 1 time dimension that we see around us. So we are stuck with higher dimensions. Specifically, string theory says that instead of the space that we live in, which is R13, instead we have, say, a 10-dimensional space that looks like R13 across a compact 6-dimensional space. This is one class of solutions. So a 10-dimensional space in which we have our universe times a compact extra dimension. You might say, why compact? Well, if it wasn't compact, we would have seen it already. And the scale of that size had better be very small to be consistent with observation. This seems like quite a big stretch, and it is. But you can say, what would be the physical consequences of this being true? And can we actually work out that physics and test whether it matches what we see in nature? Can we make predictions with string theory? So in that context, you're going to begin with Lagrangian theories that describe the low energy physics. So this is going to be a 10D Lagrangian. And in principle, you would have an S, which is some integral over a 10D space that looks like an Einstein-Hilbert term to describe gravity, plus, say, Yang-Mills terms, plus a whole bunch of other stuff. Why am I sketching this? Because obviously, if you're looking for a solution that could describe something like our universe across a compact space, you have a big multidimensional integral over 10 dimensions. If you have a compact set of dimensions in your solution, you can just integrate out this Lagrangian theory, this functional. You can integrate out your dependence on x6, and you can be left with a 4D theory. So if you do the integral over x6, then you are left with, let's say this is S10, you're left with S4, which is going to look like some d4x r plus f squared, blah, blah, blah. Now, the reason I'm emphasizing this structure is if you say, well, okay, cool, string theory is some big quantum gravity, describes all forces in nature. What physics do you actually see in a solution that could look like our world? You have to actually answer this question. You have to be able to say, what is the Lagrangian that you would produce from string theory? Now, it's very clear that this functional that I wrote down depends on the metric. It depends on the metric in a really big way. So I would have a metric on the total space, and because this is a direct product, I would also have a metric that just lives over this compact direction. That's the thing I actually want to integrate out in moving from here to here. And so if I want to say, what is the functional that I'm writing down that describes 4D physics, I really need to know the metric over x6. Where does this appear? It appears in all sorts of stuff if you work out the details of how to do that integration and how to break things down. This appears all over the place. So you need this, for example, for particle masses. For example, if you want to say, what's the mass of the electron that you would get from string theory? You need this. You need it for couplings between particles, for example, Yukawa couplings. You need it for gauge couplings. Basically, all the physics that you could imagine this touches in some way, direct or indirect. Now, this has been an issue in the subject of string compactifications for 30 years. We have a Fields medal for proving this metric exists, but we don't know what the metric is. So string theorists have been extremely clever. I'm not saying this because I haven't been doing this for 30 years. Other people other than me were very clever for 30 years in trying to think of very nice ways to work around their ignorance. So we've extracted loads of information about the low energy physics, and there are many hundreds and hundreds of papers written about particles and interactions and structure of the theory that you can get without knowing the metric, but it's a massive hurdle. So when you hear people say, well, string theory's been around a long time and hasn't made any predictions, what's up with that? The basic answer is that we need to be able to actually do calculations like this to really decide what the physics that string theory might predict would be, and we just don't know how to do them. So as I'll show you, this results in basically higher order, really awful PDEs in curve spaces that we don't know how to solve. And so until we can do that, we can't answer the question of the physical utility of things like string theory. Okay, so this is why this is a major prize within string theory. So obviously we want to know the metric, and then we want to compute lots of stuff like this once we find it. So in order to tell you a little bit about how we're going to set up those differential equations and what features of the compact space and its geometry are important, I'm going to blast through a little bit of review of what are the essential ingredients that you need to describe some curve geometry. So the main one, of course, and this enters if anybody has had courses in general relativity, the basic idea behind doing physics on some weird curved space is that you want to pick a patch of that space and pretend that you just live there. So you want to say that physics, most of it, physics is local. And that works for quite a lot. So the geometric way that you phrase that is that you're going to define a manifold, such as this one, which is determined by the data of a collection of open sets U alpha and morphisms phi alpha, which, let's say, start with real manifolds. These are open sets. And this is a morphism phi alpha, which takes U alpha into Rn, say, which allow you to take the information about where you live in the manifold, map it into Rn, and then just do your calculus in Rn, like you know how to do it normally. The catch, though, of course, is that there are global features of this geometry. For example, its non-trivial topology, as I've drawn here, that will impact lots of physical questions. For example, cosmology is something that you can't really talk about without knowing the global structure of your space. So for that, the next data of a manifold is that you need to consider what happens on the overlaps of two open sets. So if you have two open sets that have a non-trivial overlap, then you require the following. Alpha intersect T beta. You need this to be a diffeomorphism. Now, what's up with this? This is really where the global structure comes to talk to you in a big way in the form of these so-called transition functions, which map you from the coordinates and information of one local bit of physics to the next. And that says, if we're in a big giant curved space, in my patch of the universe, if I write down physics in whatever coordinate system I choose, then you move over to your patch, you do your physics. We all can do things locally, but when we need to compare answers, we need a mapping to do that. That is transition functions. Now, for the context of this lecture, we're going to be interested in complex manifolds. Sort of beyond the scope of this course to explain where this comes from in this dimensional reduction of moving from 10 to 4 that I mentioned before. But let's just say for string theory, or string compactifications, frequently, though not always, we're interested in compact manifolds, complex manifolds, and as I'll talk about today, a further feature, again, sometimes but not always, which is scalar manifolds, and I'll define what this means in a moment. So compactness, we've touched on why we care about that briefly. Let me just summarize what it means to be a complex manifold. So a complex manifold is the same idea as before. We have a set of open sets and morphisms into Rn. But the catch here is that we require the morphisms, I'm going to call them Z alpha, which map U alpha into Cn. These we require, say, this composition, the transition functions, to be holomorphic. So if we have a complex coordinate z, which is x plus iy, we require that the transition functions are a function of z only, not z bar. This is saying that the mapping of what you mean by complex numbers versus their conjugation, what you basically mean by complex conjugation, is being preserved globally as you move from patch to patch in this manifold. If you have a bit of terminology, an atlas is this collection, say U alpha, I called it phi alpha above. If I give you this information for any manifold, real or complex, that's called an atlas. And if you do this in the complex case, so choice of atlas plus the holomorphy condition in the complex case goes into the name of a complex structure. So you'll hear in geometric terminology, you'll say, does X manifold admit a complex structure? That means, can you set up this framework? Lots of manifolds. So let me back this up. If you have a complex manifold, of course, every complex manifold is a real 2n dimensional manifold, but the converse is not true. So many manifolds cannot be phrased consistently in terms of complex coordinates. So as an example, S2 is a complex manifold, which we'll talk more about in just a moment. So the surface of the two-sphere. But S2n is not, except for n equals 1. Let me just say, not for n greater than 1. So if you have 2n spheres, they're not complex except for S2. Okay, so it's somewhat special to be able to write down complex structures of things. All right, now in the context of string theory, I've mentioned already we're interested in complex compact manifolds. So just as an aside, you might say, how am I going to define compact manifolds? Well, compact spaces are very easy in Rn. So for example, I write down an equation like this in R2, manifestly compact, easy to write down, simple equation, we're set. In complex manifolds, this is much harder. So, but Cn much harder because of this holomorphy condition. So in fact, Cn admits no complex compact submanifolds. No complex compact submanifolds in Cn. The reason for this has to do with the triviality of holomorphic functions over Cn that are bounded. So if you try and just write algebraic equations like that one in Cn, things are trivial. So we need an alternative as a simple complex space where we can write down equations so that we can generate some very explicit compact manifolds. So fortunately, there is a nice alternative. So alternatively, I'm going to consider a space Cpn, or in the physics literature, this just gets, we drop the C and write Pn. This is called complex projective space. And this turns out to be a much nicer ambient space for writing down systems of equations. So what is Cpn? This is the set of complex lines through the origin in Cn plus 1. So we start with the Cn n plus 1 dimensional space. You consider a line through the origin. Obviously, can't draw through the origin apparently. I'm artistically handicapped, sorry about that. So then through the origin, I can specify any line through the origin by specifying a single point in Cn+1. And it's clear that this is defined, so this line is defined by one point, and if I have 2 points that lie along the same line, that's going to be the same point in this projective space. So the formal definition for this is that Pn is equal to Cn+1 minus the origin modulo a C star action, which says that everything along a ray is going to be the same object. So a simpler way to think about this is if I treat the coordinates of the Cn+1, complex coordinates z0 to zn, these I'm going to call homogeneous coordinates, i.e. this is the choice of the point that's going to determine the line. We say that these coordinates, the vector of such things, is the same point in Pn if I can identify them up to scale. So that's again saying they live on that same line for the origin. So this is the C star action that I am quotienting by here. So identifying the two and lambda not zero. Okay. So you're going to play with this a little bit in the tutorial this afternoon, both putting coordinate patches on spaces and also playing around with complex projective spaces of this type. So you can ask, what are the open sets on a complex projective space? So here, open sets are, for example, the UI I can define as where one of my homogeneous coordinates is not zero. And that allows me to write down my local coordinates, i.e. my mappings into Cn on UI can just be defined as the quotient, say WIK is going to be ZK ZI. So I take the coordinate that's not zero, I divide by it, and then I have a vector of the rest of the coordinates. That's a good local set of coordinates on the patch of the manifold where a given coordinate is not zero. So I can cover the whole thing that way. And this is a nice local set of coordinates. Okay. By the way, feel free to stop me if I'm blasting through something too fast. I'm happy to pause. So you're going to play with this a bit more in the tutorial. As a brief aside, complex projective space is useful, but it's by no means the only way to get around this question of like, what's a good ambient space to write down compact algebraic equations that give a compact space. So a brief aside, there are lots of other ways to do this. So a simple generalization is something called weighted projective space. And here you have exactly the same idea. You take homogeneous coordinates for a Cn+1, and instead of identifying them up to an overall scale, i.e. the line through the origin, instead you can scale each one individually. So this is an easy generalization. This also leads to a compact space. You can generalize still further by having multiple directions and scalings that vary in multiple different directions in the space. And this is under the subject of a toric variety or toric geometry. We're not going to talk about this today. But again, easy generalizations of the same idea. Okay, so the plan is going to be that I need to write down complex compact manifolds. I've defined a reasonable starting ambient space for us. Now I need to, in order to define what a Calabi-Yau is and to say what geometric features are going to be necessary for set up this PDE for the metric that I want to solve, I need to define a bit more geometric ingredients. So specifically, I need to talk a little bit about what it means to be Kähler. That was a word that appeared already in the definition. I need to talk about what it means to be Kähler and also to set up what it means to have a metric on that space, what I'm interested in that metric. So we're interested in metrics on compact complex manifolds. And for that, if we're in the complex realm, we're interested in a so-called Hermitian metric. On a complex manifold, we'll call it X, is a length interval or covariant tensor field of the form Gi J bar dzi dz. J bar. So what is up with this choice? Again, this is about preserving the complex nature of the space and achieving real line intervals out of it. So in local coordinates, we are interested in metrics that have the form that they are only of mixed barred unbarred index type. So the pure unbarred or pure barred indices components of the metric are 0. Also, we are interested in imposing that G J bar I is the complex conjugate of I J bar. And we need a positive semi-definite condition on this line interval, like so. So with such a metric, this allows you to define a differential form. So this allows you to define a real 1-1 form, which is sometimes called the Hermitian form, sometimes the fundamental form. Hermitian form. I'll call it J, which is simply the metric dzi dz bar J. Okay, why is this 1, 1? What does this notation mean? An n form measures the number of differentials in the space. So here are 2 differentials, that's a 2 form. 1, 1 tracks in a complex manifold how many indices are holomorphic versus anti-holomorphic, barred versus unbarred indices. So 1, 1 means 1 barred, 1 unbarred index on that 2 form. Okay, so this thing is called, question? I will be getting there in just a second. So this is really relevant in order to define real line intervals and distances within the space. We'll talk about, how this is appearing in various constructions in just a minute. But feel free, was there anything else you wanted to say in this context? Okay. Feel free to add. So good. So the relevant thing for today's geometry is if there is a further condition, which is that dj is 0, then this Hermitian form gets upgraded and is known as a Kähler form. We say that if a Kähler form exists on the space, then you say that X is a, quote, Kähler manifold. So what does it mean that this exterior derivative acting on this form is 0? Well, if I write out that exterior derivative in terms of the complex coordinates, obviously dj is equal to d plus d bar, gi j bar, dzi j bar, and we demand that that is 0. So this tells you a lot about the structure of this metric, which, by the way, the metric, the resulting line intervals or distances that you want to measure in the space are real, but this metric is not real or even holomorphic. So it's a function of both z and z bar in principle. But this condition tells you that the following must be true. And the same condition with the indices interchanged. And if you play around with all the differentials that have to be 0, you can show that the metric must take the following very easy form. So the metric is defined as a second derivative of some function k. So this is a function called the so-called Kähler potential. And instead of defining an n by n matrix that is Hermitian, you instead get to define everything about this metric from a single function. So that is a vast simplification of the possible geometry. The Kähler forms that you would define using first the Kähler potential, generating a metric, and then the Kähler form also have a simple relationship to an overall volume. Let me just mention that now. So it's a consequence of this structure that if you were to take the nth power of your Kähler form, that gives you a top form, an overall volume in the space, which up to some factors that I'm going to omit, looks like the following. So you will frequently hear about the choice of a Kähler form or a Kähler class for a geometry. as telling you something about volumes of the spaces. This is an easy way to see where this is related to the overall volume. It can be related to more volumes if you have non-trivial subcycles or holes in your geometry, but at the very minimum, it's that one. So it is not surprising, perhaps, that if you look for examples of Kähler manifolds, CPN, which we just defined, is Kähler. Emits a nice Kähler form. And there are many other examples of Kähler geometries in play. In fact, whole classification programs, and this is the context where Calabi and Yao were doing their studies, sought to classify Kähler manifolds with various signs to their first Chern class or curvature, things of positive, negative curvature. And you'll hear more about related geometries in the context of Fano manifolds later today, I believe. So one more thing that I need for later, it turns out that in the presence of this Kähler structure, the curvature of the space, which is going to be very important for the extracting the physics that we're at later, for any Kähler manifold has a very simple form. And this is the following. I'm not going to derive this, although they'll talk about related things in the tutorial today. So the Kähler form is simply given, excuse me, the curvature is given just like the metric is given by two derivatives. The Ricci tensor, Ricci 2 form, is given by two derivatives of the log of the determinant of the metric. Likewise, you can define something that appeared already in my definition of Calabi-Yau manifolds, and that is the notion of a Chern class. These are topological invariants for compact complex manifolds that we're interested in. Specifically, I'm going to define the first Chern class, which is basically just the trace of the curvature 2 form. A little bit more precisely, swing over here. I'm going to define C1 of a manifold to be I over 2 pi, RK L bar, DZK, DZ bar L bar, which is just 1 over 2, I over 2 pi times the Ricci scalar. And this is minus I over 2 pi UD bar log det G for the Kähler case. You'll need this for one of the problems in the tutorial this afternoon. So why do we care about things like Chern classes? These are topological or deformation invariants for the manifold. So as I define a metric on this space and then wiggle it, this quantity does not change under small deformations. Okay, so with this rather rapid set of definitions in hand, now I can tell you a little bit more about what it is to be a Calabi-Yau and why this is relevant to us. So now for Calabi-Yau manifolds, I've already given you the definition. Kähler manifold with C1 equals 0, also a thing that admits a Ricci flat metric. Kähler manifold that admits a Ricci flat metric. So Yau's theorem is the following. Yes, good. So I should say this is plus exact. So James is pointing out I was a little bit loose here. I'm giving the cohomology class of the first Chern class. That's actually going to be important for the problem that I set in the tutorial. So what does it mean to be in a given class? For differential forms, frequently we're interested in forms that are closed but not exact. You'll be familiar from exact degrees of freedom, or like the gauge freedom in electromagnetism. These are things that do not change the underlying physics. So up to exact pieces, this is the form. So as a class, that is true. Okay, Yau's theorem. So we say if X is a complex Kähler manifold with C1 equals 0, notice that's the trace of the curvature, not the full curvature, is 0, and some Kähler form J, stiffer, and some Kähler form J, then he proved that there exists an honest Ricci flat metric. That's the Ricci 2 form is 0, not just the Ricci scalar. Ricci flat metric on X, say with Kähler form associated to that one, J prime, which is in the same cohomology class, as the initial scalar choice J. This is very much related to the point James just made. So J, we say J prime is equal to J plus something exact. And in the context of complex manifolds that satisfy the DD bar lemma, you can actually prove that this is something of the following form. So the claim is if you have a Kähler manifold with C1 equals 0, you find yourself any metric, not necessarily Ricci flat, that you can admit onto the space. Then if you are in a given choice of Kähler form, so you picked yourself a Kähler class J, up to a piece of this type, there exists a Ricci flat metric in the same class. So that was Yao's theorem, and this is the thing that we're going to hunt for numerically. We want to find that actual Ricci flat metric. Okay, so moving swiftly ahead then, we have to say, how are we going to set up that problem in a way that is efficient? And to do that, we need a couple more elements of geometry, and I need to talk about how I'm going to algebraically define a Calabi-Yau manifold. So to that end, I've introduced one of the canonical pieces of geometry I need for Calabi-Yaus. Let me introduce one more. So key ingredients. The Kähler form J is important. There's also another form that can be defined very specially on Calabi-Yau manifolds. This is called a 3-form or 3-0 form for Calabi-Yau 3-folds. I should say, by the way, Calabi-Yau n-folds are what we're studying, of course, but to get from a 10-dimensional string compactification down to 40, you're interested in 6 compact dimensions, which is 3 complex dimensions. So I'm going to be focusing the rest of this on specifically the dimension 3 as a complex manifold. So in general, a Calabi-Yau manifold, and here we'll say 3-fold specifically, admits a nowhere vanishing covariantly constant n0 form in general, 3-0 form omega in the case of 3-folds. So why is this important? This 3-form can be easily derived if you study the holonomy of the space and the existence of covariantly constant spinors on the space. There's very nice forms for this 3-form. I'm going to skip those today in the interest of time. But this thing is the fact that it's nowhere vanishing and covariantly constant. This is a 3-form that is essentially unique. You can prove this 3-form up to a constant, non-vanishing constant, is basically determined by the Calabi-Yau geometry itself. And we're going to see an explicit construction of this in just a moment. For right now, the reason that I want to sort of emphasize this ingredient is that this allows you another way to define the volume. Another definition of the volume of the space would be omega bar. So this is a 3,0 form and a 0,3 form, and together they would give you a top form on the space that spans the whole plane. This is important because it is exactly the existence of these two ingredients that Yau used in his proof to repackage the Ricci flatness condition into something that was much more tractable for the analysis that he had to do to prove his solution exists, and we'll see something that's much more tractable to set this up as a machine learning problem. So to see this, recall that if you wanted, so the essential PDE in curved space that we want to solve is Rij bar equals 0. Based on the Kählerity condition that we saw, so since Gij bar is the derivative of some Kähler potential, if you tried to directly solve this nonlinear equation for the Kähler potential, this is 4th order and nonlinear. And frankly, horrible. Horrible whether you're trying to tackle it analytically, using analysis, functional analysis, using numerics. This is awful. And so Yau had a very clever idea, which is the relationship that I highlighted above here between any two Kähler forms on the space can actually allow you to repackage this condition into a complex Monge-Ampère type equation that is much more tractable, both analytically, still not solvable, but more easy to describe and bound, both analytically and numerically. So the basic idea is that Calabi-Yau-Ricci flat, if these key ingredients exist, the J and omega that I've defined, you can show that this condition is essentially equivalent to the fact that the two ways we had of defining a volume for a threefold, here the 1, 1 forms, so each of these guys is 1, 1. This is going to be a 3, 3 form, that this has to give you exactly the same answer for the volume as this construction, up to an overall constant, which is not vanishing. If you say then that for some Kähler class, this is true, so write down this top form using any Kähler class that comes to hand. Construct this top form. As we'll see, there are explicit algebraic ways of writing these guys down. If you write this condition down and you say up to a term of this type, my Calabi-Yau Kähler form must be specified. You can treat this now as a second order equation for phi. And this is exactly what Yau did in his proof, which made things a lot easier. So we'll come back to that in the context of the setup for machine learning in just a next lecture or two. Other things to mention. The proof due to Yau says that in a given Kähler class, the Ricci flat metric is unique. That's a little bit misleading because Calabi-Yau manifolds have moduli. Specifically, if you say, what is a modulus? If I start with some metric G and I consider, this is Gij bar, I consider perturbing it by some change delta G, I can ask what fluctuations of the metric are allowed. So the easy one is that you can consider perturbations of 1, 1 type. So you can consider delta Ij bar. These are fluctuations of the underlying Kähler class or Kähler form of the manifold. So these are called Kähler fluctuations, so called because it's clear that if I consider something of this type that is closed, then this is going to continue to preserve the Kähler condition and the Kähler form of the Hermitian metric. And so this changes nothing in the geometry. This is an allowable fluctuation. You can also have fluctuations a little bit more subtly that are, for example, a pure barred or unbarred type. Now, those are a little bit more dramatic as a fluctuation because you're moving away from the Hermitian or the Kähler condition. And so you might say, what is a fluctuation of this type going to do? Turns out that if you do certain fluctuations of this type, you can choose new coordinates to put things back into the Hermitian Kähler form. Fluctuations of this type are allowed, but they change the underlying complex structure of the manifold. We'll see in the algebraic context in just a moment, these have a very simple interpretation when you write an explicit set of equations that define a Calabi-Yau. These change the shape of your manifold. These change the size or various volumes of your manifold. So there are allowable fluctuations. So when we say that the Ricci flat metric is unique, that means you have to fix a Kähler form and you have to fix the complex structure, and then you have a unique Ricci flat metric. Okay. So with my remaining few minutes, I need to just define now how are we actually going to write down compact Calabi-Yau manifolds, and then we're going to, in future lectures, try and build some metrics on them. So for that purpose, let's build some simple Calabi-Yaus. And sort of asides on this, although the geometric study of Calabi-Yau manifolds or geometries like them, as I mentioned, originated in the 50s, culminated in Yau's proof in the 70s. This has been of interest to geometers for a long time. The explicit construction of Calabi-Yau manifolds is something that physicists have really contributed to and built very large data sets of much more recently. So the idea is that we want to consider algebraic constructions. Just like I defined a circle as an equation in R2, you want to write down a compact manifold, and you'd like to do it through some system of equations. So algebraic constructions, what am I interested in? As I've already mentioned, I introduced complex projective space to give myself a nice ambient space. So as an example of such an algebraic construction, suppose that I wrote down a holomorphic function equals 0 inside Pn. I can ask, what does it take to make that Kähler and Calabi-Yau? First, as a comment, it is important to note that in order for this equation to make sense with the underlying scaling of a CPN, this had better be a homogeneous equation, i.e., things like z0 squared plus z1 squared equals 0 makes sense because if I scale all these coordinates, that's the same point in CPN, right? Here, everything would scale with the power of 2. That would drop out of my equation. That's sensible. If I tried to write down something like z0 squared plus z1 equals 2, that is a meaningless thing inside CPN because these guys would scale. This would scale like lambda 2, lambda 1. That doesn't scale. This makes no sense. So we're going to write down homogeneous polynomials or functions inside CPN. So first claim is that it is easy, and you'll get to play around again a little bit with this in the tutorial, easy to show that algebraic subvarieties like this are Kähler. So if you start with an algebraic subvariety of a Kähler manifold, the Kähler condition for the restricted metric comes very rapidly, and that's easy. So Kähler is straightforward, but I need Ricci flat or C1 equals 0 Kähler in order to guarantee Ricci flatness. So I can ask, how am I going to achieve C1 equals 0? This is, again, something that you're going to look at in the tutorial. But we can use the form of the first turn class that I sketched for you already. You can show that for a simple hypersurface in CPN, beginning with some metric on CPN, specifically, I'm going to take a canonical one that looks as follows. We'll hear more about possible choices of this regard in future lectures. Say this guy is a nice Kähler metric, clearly defined in terms of a Kähler potential, which is all this junk in this case. This is the so-called Fubini-Studi metric. If you begin with a metric like this, you can then ask what happens when I restrict said metric to the p equals 0 hypersurface in this space. So here I have Pn as my ambient space. Here's an equation given by p equals 0 algebraically inside it. We can restrict metric to x defined by p equals 0. And if you do that, you will find that the Ricci-2 form that you get from restricting the Fubini-Studi metric to x has the following form. I said already that I needed a fixed scaling degree for these equations. So let me demand that this is a polynomial which is homogeneous, as we described, of degree m. So in this case, this would be degree 2. Everything scales with the same power. So you can show that if you have a p of degree m, that this takes the form n plus 1 minus m d Fubini-Studi plus total derivative terms. This is enough to show you up to, again, the class, the cohomology class condition that we've written down before, that if n plus 1 is equal to m, then C1 equals 0, and we are in the right topological ballpark to admit a Ricci flat metric. So a very first example that everybody writes down, imagine that I start with P4, CP4, and a degree 5 hypersurface therein. For example, suppose that P of Z is Z0 to the 5 up to Z4 to the 5 equals 0. This is the so-called Fermat quintic. sorry, this is too low. This is the Fermat choice. Then this will lead to X with C1 equals 0, i.e. X is Calabi-Yau. Clearly, this is not the only choice I could make, though, for something like this. So here I chose a very particular degree 5 polynomial in order to get the first Turing class to vanish. You could ask, what other ones could I choose? So alternative choices in this case, I could write down a P that looks like alpha, Z naught to the 5 plus beta, Z naught to the 4, Z1 plus blah, blah, blah. And I can say, how many different degree 5 homogeneous polynomials could I write down? That is a simple combinatoric problem to work out. So it is straightforward to check that there are 5 plus 4, choose 4, which is 126 possible coefficients that I could write down for a polynomial equation of this type. However, not all of them are different because I'm not interested in things that are the same up to coordinate redefinitions. So there are, in fact, 24 PLG 5C coordinate transformations that I could, that will give me the same algebraic equation. And it's clear from a polynomial of this type, because I'm equal, this thing equal to 0, there's one overall scale that's going to drop out of that equation. So I don't want to change the coefficients up to overall scale. So there's also one scale. And so this leads to a total of 126 minus 25, which is 101 possible coefficients to this complex Kähler C1 equals 0 manifold. Turns out that it is easy to, not easy, it is possible to show that these 101 parameters that change the algebraic form of the hypersurface are in fact complex structure of the manifold. So these map exactly to fluctuations of the type, pure barred unbarred. Yes, sir.
What's PLG again? Sorry.
Projective. So these are like GLN transformations, but in projective. Other questions? Great. Okay. There's also, in this particular simple example, you can show that every Kähler form in CPN is proportional. And so there's actually only one Kähler modulus direction. I'm not going to prove that in this case, but there's actually one degree of freedom that is the Kähler modulus. So these are fluctuations delta G I J bar. There's one overall scale that is possible here. This is the overall volume of the space. So again, these guys are shape. You can see you're changing the shape because you're cutting out. That's too far up there now, but if you look at the P equals 0 hypersurface I wrote up there, you're just changing the shape of that algebraic slice that you're making in the space, and you can change the volumes. A bit more fancy, these are elements of H11X. These are elements of H21X. So these are the two independent Hodge numbers for a Calabi-Yau threefold, in this case, 101. Okay, so it should be said at this point that this was a single hypersurface in P4. This is the easiest thing I could write down. It is by no means the only one. So a bit of notation, people write down for a single projective space and a polynomial of a given fixed degree, we might write this. So this is a P of homogeneous degree M in the space. So this notation, I would write down P4 and in the brackets 5 for the manifold that I just defined. So this is called the quintic threefold, quintic for the degree 5, and is the easiest Calabi-Yau that we have ever found. But you can write down lots of others in the same notation. An obvious one is you could start with a bigger projective space and define more equations to lower the dimension. So for example, I could start instead of P4, I could start in CP5 and write down 2 equations, each of degree 3. You can show, again, looking at the form of the restricted metric and its curvature, you can show this has also got C1 equals 0. You could write down things like P5, a degree 4, and a degree 2 equation. So this is P1 of degree 3 equals 0, P2 of degree 3 equals 0. And the same here for 4 and 2. You can also take products of such spaces, so products of CPNs, and write down homogeneous equations in those. You can use weighted projective spaces, and you can generalize still further to these toric varieties. I should mention that in the history of this, in the I remember the exact year, late 80s, early 90s, there was a data set of products of projective spaces and algebraic complete intersection manifolds, so complete intersection Calabi-Yau's that were defined by Candelas et al. And this was about 7,000 manifolds. This was the first big data set of Calabi-Yau's that people played with. And then this was generalized still further in the 90s. If you consider toric hypersurfaces, these are more general ambient spaces. There are now about 500 million of those that have been constructed, which is a very rich arena as a set of topological spaces for machine learning. Yes. Did I write them exactly the wrong spot? Yes, I did. Thank you. Sorry. Helps if you write the right thing in the right spot. Thank you for that. This is a stiff word. Okay. I would just say that I'm weak, but I was much stronger on the other board. Okay, there we go. This data set was constructed by Kreutzer and Skarka. And again, it's a very nice playground for lots of computer problems, because obviously you're not going to analyze 500 million manifolds by hand. And so this is very a rich arena for computational techniques. For my last 5 minutes, I need to tell you one more thing that we're going to need. Yes?
From a physics standpoint, is there a reason to prefer one manifold to the other?
That is a great question. The short answer is, unless I have the capacity to fully determine the physics out of these compactifications, I don't know. So an argument that has been made against string theory is that you have a lot of Calabi-Yau's. You might ask, is it known if the data set is finite? Could there be an infinite number? We do not know. We don't know if it's finite. We don't know if there's a finite number of topological types. And we don't know the physics that might be relevant for describing our world from that data set. So to answer that question is difficult. It might be that none of these describe the physics of our world, in which case this is not the right class of geometries, or maybe string theory just in general is not set up to describe physics for universes like ours. That's a possibility. The fact that there's a ton of these, though, is not totally surprising. So let me give you a sort of related comment. In quantum field theory, we know how to write down an infinite number of quantum field theories that are not the standard model that describes the interactions we see in nature. That doesn't matter, because we know how to write down some quantum field theories, like the standard model, that do a really good job. The issue with string theory is that we just don't know yet what the rules are for which geometries we're interested in. And that's part of where machine learning techniques and being able to solve some of these equations would be very powerful, in that it would allow us to filter what we're looking for in a much more robust way. At the moment, we don't know. You will hear lots of things, and perhaps I've heard of string theory about 10 to the 500 vacuum string theory can't ever be predictive. I will point out that computations like that people have played with have been in sort of toy geometries or toy string compactifications where we could try and describe the vacuum, not necessarily ones that describe our universe. So the 10 to the 500 number actually consists of a set of string solutions, none of which have an electron in that vacuum. So again, depending on what you're interested in, it doesn't matter. We just need more computational control of the theory before we know how to answer that question. So it may be totally useful, it may be totally empty, we just don't know yet. A good question. Other questions at this stage? Okay, so last technical thing I will tell you in 2 minutes, and then we can chat more broadly. In order to set up the numeric constructions to try and generate a Ricci flat metric, I told you before that we wanted to use this Monge-Ampere type equation where we're essentially relating volume. So volume in terms of a Kähler form, a volume in terms of the holomorphic 3 form. For that, it turns out that there's a very nice explicit form for the holomorphic 3 form for algebraic manifolds like this one, and this was developed by Candelas et al. So I want to just briefly give you the form of omega on a complete intersection Calabi-Yau. Complete intersection means complete intersection of all those algebraic equations. So if we have a Pz equals 0 hypersurface inside Pn, as we had before, then you can show that the following object is a nowhere vanishing holomorphic 3 form. What do I mean by this? Here, mu is equal to a fully antisymmetric thing on the ambient space where I'm defining this hypersurface. Let me write this. Okay. Missed one term that I need. So on the ambient space, I'm going to work on a patch where one projective coordinate is not vanishing. That's how I defined open sets. And on that patch, I'm going to write down the closest thing I can get to a top form, which is to write down the wedge of all the differentials, omitting one. So this hat notation means I'm going to omit this differential. And instead, I'm going to add a undifferentiated copy of it in the front with the fully antisymmetric tensor density out here. Why on earth would this be the right thing? Also, what do I mean by this gamma? This is a contour. So here's my p equals 0 hypersurface, and for the complex integral I'm going to do, gamma is a contour that surrounds the p equals 0. The derivation of this relies on things that were developed for Riemann surfaces in lower dimension and is quite nice, but the sort of obvious guess for why such a thing could be sensible is you can play around with how these things scale, and by construction, these both have to scale in exactly the same way so that this quotient is well defined. This is basically the only holomorphic thing that you can write down that won't vanish on the p equals 0 hypersurface, and the two pieces scale the same way. Things that I want to say about that. So this quantity mu scales as n plus 1, n from the differentials that I'm actually including, plus 1 from the prefactor out front. Obviously, the n plus 1 condition is the Calabi-Yau condition for p. That's the degree of the homogeneous degree of this equation. This is manifestly holomorphic. To prove that it's nowhere vanishing is we're going to require more time that I have, and I'm out of time. But you can write this very explicitly on a given patch. The reason that's going to be very useful, as I've mentioned before, is that we want to repackage the Ricci flat constraint as this Monge pair equation. J cubed is omega wedge omega bar. This is the actual equation that we're going to try and teach a neural network. Here, the Kähler form is very explicit. If you can write down any Kähler metric, not necessarily the Ricci flat one, and now, thanks to an algebraic construction of this type, we can write a very explicit form for the right-hand side as well. I'm out of time, so let me pause there, and James will pick up with this further tomorrow. But I'm happy to answer any questions.